In this video, I'm going to be introducing my project to develop a miniature, multi-purpose smart home device before giving a short demonstration. The Internet of Things market is rapidly growing. Several widely available and popular devices can measure or control anything from light to temperature to motion, with many users becoming interested in developing their own smart home device. There are few existing multi-purpose IoT devices which allow a user to easily swap in different sensor modules, and those which can are typically difficult for a beginner to use or only allow compatible modules to be used. The motivation of this project was to design a low-power, portable, plug-and-play style IoT device which could be used to connect a sensor and customize the device for a particular function. Design and implementation. Before implementing the PCB design, any analog circuitry was simulated in multisim to ensure that the selected components would be suitable for use. The simulation data could later be used to verify that the circuits performed as expected. An overall block diagram and specification were then derived, and from this, components could be selected keeping in mind the cost, size, and low power requirements. The device is compatible with a wide range of sensors, including analog, digital, and I2C, and has 4 available wake-up event triggers, including a digital interrupt, detecting an analog signal threshold, detecting an analog signal change, and a timer. The device can be set into a variety of states, which each consume different amounts of power. These were modelled using datasheet values to give an expected battery life for the device. A summary of the current draw for each state can be seen here, since the operating modes using Wi-Fi draw over 100 times more current than the deep sleep modes. This shows the importance of operating in a heavily duty-cycled manner, where the device spends most of its time in deep sleep and only wakes the microcontroller when data is ready to send. The PCB schematic and layout were then designed using Eagle. The embedded software was developed for the ESP32 microcontroller. As shown in the flowchart, the ESP32 remains in deep sleep until a wake-up event is triggered by the sensor or one of the buttons. If a sensor event was triggered, depending on the configuration settings, either an ADC reading, an I2C sensor reading, or a string will be sent to an HTTP request to IFTTT webhooks. This triggers an action set up by the user, such as an email, spreadsheet update, or notification containing the data. This leads to the final product. The PCB was manufactured and the components assembled. A screw terminal was added to connect sensors to the board. This features analog, digital, and I2C connections, as well as ground and 3.3 volts. Due to issues with the selected DAC module, 2 DACs were also connected to the I2C terminals. To test and evaluate each of these elements of the device, test cases were derived to demonstrate the performance of the device. Since the device can integrate with a very wide variety of sensors, it would not be feasible to test the device in every possible use case. To measure the current during the tests, a multimeter was connected in series with the battery in the board. The user can then press the Wi-Fi setup button, which starts the ESP32 as a wireless access point. From here, the user can connect to the device as a hotspot. Entering the router IP in a browser connects to the web server, which can be used to detect which device is in use by toggling an LED and allows the user to enter their network SSID and password. The user should then visit IFTTT to set up the webhooks applet. In this case, we are storing the sensor value in a Google Sheet. The user can then get the unique URL that the HTTP request will be made to trigger the IFTTT event. This can then be entered into the configuration user interface, which allows the user to choose the interrupt option, the type of data to send, the unit, the multiplier, and offset, which can be saved or published directly to the MQTT topic. Pressing the config setup button subscribes to the MQTT topic and gets the configuration JSON. An analog temperature sensor was then connected to the board, and temperature readings could be taken using a digital interrupt supplied by the button. The device can be set up for a variety of functions, some of which are demonstrated here, including detecting a voltage change, detecting a voltage threshold, taking a temperature reading, or taking periodic readings. In this example, the device takes a reading every 30 seconds. With a low-power sensor and configuration, the device could run for multiple months. These were the measured currents for different device states with no sensor plugged in. The measured current was lower than the expected current draw, likely due to deviations from the datasheet currents, particularly the ESP32 power modes. Therefore, the power consumption of the device was better than expected. The latency between an event trigger and the IFTTT action was also measured, which was usually around 10 seconds for all tested actions, which is good performance for a home IoT device. Thank you for listening.